6.2 linear relations, colon, and introduction. So today what we're going to be doing is we're going to be just starting the idea of turning patterns into equations. We're going to start off by noticing patterns in square tiles and creating a chart. We're then going to put it into a more tangible example, more real-life example with setting up tables. And then what we're actually going to do is we're going to take words and we are going to create an equation from that. So there will be equation creation, however, we're going to take a few days to convert from this chart, this T-chart that we'll get to an equation. All right, let's start. Patterns are all around us. No, I'm not going to talk like that. Don't worry about it. But actually, patterns are all around us. Here's a pattern made from square tiles. So when we notice from figure 1 to figure 2 to figure 3, what stays the same in each figure and what changes? What stays the same, this is going to be what we call our constant, because it remains constant. This right here, the thing that changes is going to be multiplied by the dependent variable. Now, I'm introducing some words here that we'll flesh out tomorrow a little bit more. We don't need to know that vocabulary to be able to do today's lesson. So the variable always resides in what changes, and our constant is always what is constant, or what doesn't stay the same, or what stays the same. So if we look at these three here, we notice that the 6 yellow blocks. And what changes? The height, which is the orange blocks. Now you won't be able to tell that on yours, but you can identify in some way in your notes what stays the same, what's different. So how can we determine the number of square tiles in any figure in the pattern? So what we have to start is a chart. So right here, this is where our independent variable. Oh, and actually I should say this is not multiplied by the dependent variable. I should say it's multiplied by the independent variable. Sorry about that. And again, we'll flesh that out tomorrow. And this right here is our dependent. Now, the independent is a value that we can choose at random that we plunk into an equation. The dependent is the answer that comes out of it. So the dependent depends on what we choose for our independent. So when we talk about the total number of blocks, that's going to be our dependent. We're going to call that T. And we always have to define our variables. T equals total number of blocks. And I'm going to say F, which is our independent, is our figure number. Now I'm going to start out, I'm going to leave one space here, and I'll tell you why in a bit. But in figure 1, we have 1, 2, 3, 4, 5, 6, 7 blocks. In figure 2, we have 1, 2, 3, 4, 5, 6, 7, 8 blocks. In figure 3, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks. And I bet that if we wanted to, we could say figure 4 is going to have 10, figure 5 is going to have 11, figure 6 is going to have 12. I want to ask you something here though. What do you think that figure 20 is going to have? Think about it. Well, if I start it with our constant, so I'm going to call this our 0th figure. Our 0th figure kind of represents the thing that stays the same. The thing that stays the same is the 6 yellow blocks. So we're going to call this 6. So with the 20th figure, well, with the first figure we say 6 plus 1, which is the figure number. With figure 2 we have 6 plus 2, which is the figure number. So with 20, we're going to say 6 plus 20 is 26. So there will be 26 blocks in the 20th figure. Now we did this kind of logically. Okay, we kind of followed a few little steps, but when we create an equation, it's going to make that process very slick. You're going to get an equation, and you can substitute a value in for the independent variable, and then you can actually calculate that. It formalizes what we just kind of did together.